Welcome back to Aurora Tech Channel. Today, I'll be reviewing a 100-watt MOPA fiber laser from Monport, which is the most powerful model in their GA series lineup. As a MOPA fiber laser, it supports a much wider frequency range than standard fiber lasers and features an adjustable pulse width, something regular fiber lasers don't offer. This gives you greater control for color marking and high contrast engraving. With the stock focusing lens, the working area is 175 by 175 millimeters. You can swap out the lens to change the effective focal length, which lets you increase the working area or adjust power density. The machine weighs over 50 pounds. The required table space is about 15 by 20 inches, and you'll need to add another 5 inches to accommodate the cables at the back. Vertically, it stands about 26 inches tall. It uses a galvanometer scanning system, which moves 2 mirrors to reflect the laser beam. This setup allows for extremely fast engraving, up to 10,000 millimeters per second. The laser spot size is as small as 0.01 millimeters, enabling highly detailed work. In addition to manual focusing, the machine also features an autofocus sensor on the platform. Once the material is placed, you can press the focus button and the laser head will automatically adjust its height. The laser head arm can also rotate 90 degrees, making it easier to engrave taller objects that don't fit on the base platform. Optional accessories include an enclosure and a rotary roller. In this video, I'll test various types of metal, show both 2D and 3D engraving, demonstrate color marking, and try out the rotary roller. I would like to thank Monport for sending us this machine to review. With that, let's get started. The machine arrived in a wooden crate with the entire unit securely protected by foam. It comes as a one-piece setup, so all you need to do is secure the Z-axis to the base using 2 thumb screws and lift the whole machine into place. In addition to the machine, there's a box containing all the necessary cables, safety goggles, tools, and a USB drive, which includes the software and machine profile. At the back of the unit, you'll find a USB port to connect to your computer, along with the power input. There are also extension ports for a rotary roller and enclosure. On the side of the machine, there's a label with key parameters. We'll use that later. Since I'll be using Lightburn instead of the included software, I'll start by importing the device profile from the USB drive. Then, I'll enter the parameters listed on the black label. Go to the device settings section. Keep in mind that each machine may have slightly different values, so you might need to adjust these numbers accordingly. For a quick test, I'll use a coded marking card to make sure everything is working. You can adjust the laser head manually or use the autofocus button. In this case, we need to move the card down slightly to the autofocus position. The machine will then move the head up and down to find the correct focus point. Next, I'll engrave a simple logo. The firmware's top speed is set to 7,000 millimeters per second, so I'll use the maximum speed with just 10% power, as this type of card can be engraved at very high speed. After drawing a preview frame and aligning the card, everything looks good, so I'll start the job. In line mode, the engraving completed in just 1 second. I then flip the card over and tried again using fill mode. This time, it took 24 seconds. Here are the results. I haven't fine-tuned the parameters for this quick test, but everything appears to be working normally. I'll now test some sample-coated aluminum business cards. I'll start with 1,000 millimeters per second speed and 10% power. If you're coming from diode or CO2 lasers, you might not be familiar with frequency and Q-pulse settings. Standard fiber lasers typically allow you to adjust the frequency within a limited range, such as 20 to 80 kilohertz. A MOPA laser like the one equipped in this machine allow a wider range from 1 to 3,000 kilohertz. I made this simple scratch animation. It may not perfectly illustrate how it works, but I hope it gives you a rough idea. For frequency, the higher the frequency, the smaller the energy per pulse, but more pulses are delivered in the same amount of time. This is generally better for light surface engraving and fine text or images. With regular fiber lasers, the pulse width is fixed. MOPA fiber lasers allow you to adjust the pulse width, giving you greater control over marking quality, depth, and even color. A longer pulse width means each pulse delivers energy over a longer time, allowing more heat to spread into the material. This results in darker marks, especially on materials like stainless steel, which we'll try later. Since we only want to burn off the coating on the aluminum business card, we'll use a higher frequency and a shorter pulse width. I'll start with 150 kilohertz and 60 nanoseconds. I let it draw a preview frame, aligned the card to the center, and started the job. It took about 44 seconds to finish. It seems the coating layer didn't burn off evenly. There are a few things we can do to improve it: increase the power, slow down the speed, use a longer pulse, or reduce the interval for higher resolution. For now, I'll change just one variable, setting the interval to 0.01 millimeters to increase the resolution. This will also slow down the job since the resolution is now 3 times higher. This time, it took a little over 2 minutes to finish. Increasing the resolution takes longer, but it makes a big difference. Next, I'll engrave a photo on the same coated aluminum card. I'll keep the speed, power, frequency, and pulse width settings the same. For resolution, instead of entering a line interval, I'll set it to 600 dpi and let the software calculate it automatically. For the engraving mode, I usually choose between Atkinson, Dither, and Stuckey. I'll try all 3 and compare the results, starting with Atkinson. Using Atkinson mode, the engraving took 1 minute and 24 seconds. I'll now run the other 2 modes and compare the results. The time difference on this small image isn't very significant. Personally, I think Atkinson delivers the best result in terms of detail and contrast. Next, I'll refocus the machine to engrave on a stainless steel sheet. With stainless steel, different laser settings can produce a range of darkness levels and even colors. You can achieve various effects by adjusting combinations such as power with interval, power with pulse width, or any other setting that affects how energy is delivered and spread. In general, the power and pulse width combination tends to work best for producing a wide range of stable colors. I'll start with 20 to 40% power and a pulse width between 10 to 100 nanoseconds. The speed will be fixed at 1000 millimeters per second and the frequency at 200 kilohertz. For the line interval, I'll begin with a faster test at 0.05 millimeters. Using a 0.05 millimeter interval runs quickly, but we can only see different shades of brown and some light silver or white tones. So next, I'll run the same image again, but reduce the line interval to 0.0025 millimeters, which increases the resolution 20 times. With this higher resolution, the laser deposits more heat onto the sheet, causing it to start warping. I should have used clamps to hold it down, but I'll let it finish anyway. This time, we start to see a broader range of colors. Since going above 30 to 40% power doesn't significantly change the results, I'll do another pass using up to 30% power and an even higher resolution of 0.001 millimeter line interval. This time, I'll use the included clamps to prevent warping. The results show a noticeable increase in color variety. I'll use the settings from this test pattern to create a multicolor engraving in Lightburn. I'll make a Hello Kitty design with 5 colors. For the dark outline, using a 0.001 millimeter interval took too long. Just the outline took over 31 minutes. If I only want a dark color, there are much faster options available. The rest of the colors took 17 minutes, so the total job finished in under 48 minutes. While the 0.001 millimeter interval gives solid color and high resolution, I wanted to try a faster alternative. Using some faster settings from the 0.05 and 0.0025 interval test patterns, I ran the same job again. This time, the outline took only 38 seconds. and the rest of the colors took about 8 minutes, finishing the entire job in just 9 minutes, over 5 times faster. When comparing the results, the 48-minute version definitely looks better, but with a powerful 100-watt MOPA fiber laser, you have the flexibility to balance between quality and speed depending on your needs. Up next, we'll test engraving on aluminum. Unlike stainless steel, aluminum doesn't produce a wide range of colors, only lighter and darker shades. So I'll run a test using a 0.01mm interval, 500 millimeters per second speed, 300 kilohertz frequency, and power ranging from 20% to 60% with pulse widths from 50 to 100 nanoseconds. As expected, the results show varying levels of darkness on the raw aluminum. I'll use this test pattern to pick some settings for engraving a logo. While aluminum can't produce colorful effects like stainless steel, being able to engrave with different shades at high speed is still useful. I'll also test brass, this time with a 3D project. Instead of a flat 2D engraving, I'll make a 3D brass Bitcoin. The settings will be 2000 millimeters per second speed, 90% power, 40 kilohertz frequency, and a pulse width of 350 nanoseconds. In Lightburn, I'll use the 3D sliced image mode and slice the grayscale image into 200 layers. After that, I'll also run a cleanup pass. I might not run it together with the 3D engraving since I may need to adjust based on the result. The job finished after 48 minutes, but the surface looked a bit dark, so I ran 2 quick cleanup passes. After that, the coin looked much better. I used a 0.03mm interval for this test. It would look even more detailed with 0.01mm, but that would take about 3 times longer. I actually tried that, but it turned out to be a mistake. Using the same power in a 0.01mm interval, the machine was too powerful and ended up over-engraving the coin. It looked like a Stone Age Bitcoin from 1,000,000 years ago. Still, it's pretty cool to see that the machine is capable of engraving so deeply on a 2mm brass coin. Finally, I'll test out the rotary roller. This machine supports different types of rollers. The one I have is a taller model with adjustable angles. However, I found it a bit too tall for engraving objects like this pen holder. The cheaper model on their website, which doesn't have angle adjustment, actually seems to fit better for this kind of job. For now, I just placed the roller on the table and raised it with a box. I started by testing it with a 3D printed part to calibrate the steps per rotation and align the engraving direction. It seems to engrave quite well on PLA. Next, I'll use a real stainless steel mug with a vinyl-coated surface. The roller uses 12,800 steps per rotation, and the mug has a 72.5mm diameter. To avoid melting the vinyl surface, I'll start with low power, 4,000 millimeters per second speed, 20% power, 60 kilohertz frequency, and a 100 nanosecond pulse width. I'll also apply 5 passes at this setting. The preview in Lightburn only shows one section at a time, since the machine engraves a segment, rotates the mug, then engraves the next segment. As you can see, the initial overlap between sections wasn't enough, resulting in visible gaps. I let it finish anyway. Afterward, I changed the overlap setting from 0.1 millimeters to 0.2 millimeters and ran the job again. With 0.2 millimeter overlap, the gaps were completely covered. Since I used low power with multiple passes, it gave me more flexibility to fix errors, and the final result looks great. After the second run, you can't even tell there were any gaps in the logo. Let's talk about the pros and cons of this machine, starting with the pros. 1. The setup is simple. The whole machine is a single piece with no assembly required. It works great right out of the box. Even though it's an industrial machine, it's actually more user-friendly and easier to use than most consumer-grade laser engravers. 2. This is a robust machine. Built entirely of metal and weighing over 50 pounds, it feels like a tank. It's a noticeable step up from the consumer-grade machines I've tested before. 3. The 100-watt MOPA laser is powerful. It can engrave on almost any metal, except perhaps highly polished surfaces that reflect the laser beam like a mirror. The engraving speed is impressive, especially for 3D work. Creating a coin like this with a consumer-grade machine would take 3 to 4 hours, but this one can finish it in under an hour. 4. The autofocus is very accurate. There's a label on the side of the laser head indicating a focal distance of 334 millimeters, and no matter what material I use, the autofocus nails it every time. The preview also creates an exact outline of your job, making alignment super easy. It definitely works better than any fixed camera system on consumer laser engravers. 5. The lifespan of a fiber laser is 5 to 20 times longer than that of CO2 and diode lasers. The manufacturer claims a lifespan of 100,000 hours, so theoretically, even if you ran it 24/7 nonstop, it could last for more than 11 years. 6. The laser head arm can be rotated 90 degrees, so if you have taller objects that don't fit on the machine platform, you can place them on the ground or a table. Technically, this means there's no height limit for the objects you want to engrave. Now for the cons. 1. Like all fiber lasers with a galvanometer system, this machine isn't ideal for cutting. It's designed for speed, not for staying on one spot long enough for deep cuts. The small beam size is great for detail, but not for cutting, and there's no high-pressure air assist to clear molten material. While it can cut thin materials like 0.2 millimeters aluminum, thicker metals like 0.5 millimeters, and thicker stainless steel require too many passes, leading to warping and burnt edges. 2. When setting up the machine in Lightburn, you not only need to import the profile, but also manually enter the parameters listed on the plate attached to the laser head. Since each laser is manually calibrated at the factory, why not pre-enter these customized values into the Lightburn profile for each individual machine? That way, users can simply import the profile and start using the machine right away. In conclusion, this is a well-built industrial-grade machine that's ideal for shops or anyone looking to use it for business. Beyond its higher power and speed, it offers the flexibility to change lenses for different working areas and power density, and it also lets you fine-tune every parameter, like shooting with a professional camera in manual mode. In comparison, a consumer-grade machine is more like a point-and-shoot camera. If you're interested in stepping into the world of professional MOPA fiber lasers, but the 100-watt model doesn't fit your budget, you can definitely consider the 30-watt or 60-watt versions. They offer the same robust build and features at a lower power and price point. I included a link to the Monport website in the video description. This machine also ranked number 1 on my recommendation list at auroratechchannel.com with the title of Best Performance MOPA Fiber Laser Engraver. My website tracks prices for popular 3D printers, laser engravers, and CNC machines. Check it out to find great deals. That's it for this video. If you found this video helpful, please give it a like and consider subscribing to our channel. Thank you for watching, and I will see you next time.